Hi, it's Laura again with the McDougall-Little Geometry Textbook, and this is lesson 10.3. We're still talking about circles, and this is inscribed angles and polygons. Inscribed polygons. All right, so what is an inscribed angle? It's an angle that's inside a circle. It's that simple. And it intercepts as it crosses the circle here at each point, at 2 points. There is an intercepted arc that is formed. So we have an inscribed angle and an intercepted arc. And what we need to know is that for an inscribed angle, that it is half the measure of the arc. We learned before about a central angle. So for a central angle, here, arc AB, for the central angle, if the angle is 100 degrees, the arc is the same. It is 100 degrees. But if we have an inscribed angle, angle D here, or ADB, then this arc is going to be, if it's 100, the inscribed angle will be half of that arc. Very simple. So if we look at this, example 1, you should be able to do these. It should take no time at all. All you have to do is remember that the inscribed angle is half of the measure of the arc. So go ahead and find the measure of the blue arc or the angle, whichever is noted, and pause, and we'll check your answers in a moment. Okay, I'm going to move on to the answers, and here they are. If this is a 90-degree angle, noted by the right angle symbol right here, that means the arc has to be twice that. So it is 180 degrees. Here we know that the angle is 115 degrees, so the arc has to be twice that, so it's 230 degrees. Here we are told that the arc is 100 degrees, therefore the angle has to be half that, which is 50 degrees. I'm sure you just flew right through those. Now, they're going to just make the pictures a little bit more complicated for you. Find the measure of each angle. You can tell by the beautiful colors that have been used. Go ahead and pause, and we'll get to the answers in a minute. Okay, here come the answers, and ta-da! They're all the same. Why? Because here is the intercepted arc, and it is 60 degrees. So all of these inscribed triangles are using the same arc, and therefore these inscribed triangles are all 30 degrees. I'm sure that you didn't have any trouble with that one. Moving on. Theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. Okay, what does that mean? Simply, if arc AB is 80 degrees, then each inscribed angle is 40 degrees, making them congruent. Very much common sense. So, example 3, pause. Given what we know right now about our theorems, and that the measure of angle E right here is 75 degrees, what is the measure of angle F? Don't forget to pause. Okay, here come the answers, or the answer. Well, they both share the same intercepted arc, so angle F is also 75 degrees. I'm sure that was not a challenge for you at all. This seems to be all very basic, so it should not be a problem. The next problem, however, is a little bit more of a challenge. You're going to have to think about it, but remember, the chapter is about circles. So there's a hint for you coming up. Example 4. When you go to the movies, you want to be close to the movie screen, but you don't want to have to move your eyes too much to see the edges of the picture. If E and G are the ends of the screen, and you are at F, the measure of angle EFG is called your viewing angle. So you decide that the middle of the 6th row has the very best viewing angle. But if someone is sitting there, where else can you sit to have the same viewing angle? Don't forget, we're talking about circles here. Give it a try, and think about intercepted arcs and everything that we have learned about those. So pause now, and we'll get to the answer in a moment. Okay, all you had to do was sketch a circle, because all of the inscribed angles on the circle share the same arc right here. Once you've drawn this circle, that means that any seat that's on this circle right here will give you the same viewing angle. So you could sit a little bit in front. I still don't know that I would want to sit way over here, but it would still be technically a great viewing angle, or the same viewing angle. Let's move on. Some technical definitions. We have inscribed. We know what that is from an inscribed angle, but also polygons can be circumscribed inside a circle. So, or can be circumscribed around a circle, or inscribed within a circle. So technically, circumscribed is a figure around another. So this circle is circumscribed around the 1, 2, 3, 4, 5 pentagon. The circle is circumscribed around the pentagon. At the same time, inscribed is a figure within another, so that their boundaries touch but don't intersect. And so this pentagon is inscribed in the circle. The circle is circumscribed around the pentagon. They're just a flip-flop of the same definition. Knowing that, however, we're going to have some theorems. This one says, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. What's supplementary? 180 degrees. That simply means that these opposite angles of a quadrilateral, 4 sides, that is inscribed inside a circle, these opposite angles will equal 180 degrees. So E and G and F and D, if you add them together, they will have to equal 180 degrees. Let us use that right now. Example 5a, find the value of each variable. Given what we know now, don't forget, pause, and I'll get you the answer in a moment. Ready for the answers? Okay, we know that D and F have to be 180 degrees, and E and G have to be 180 degrees. So for E and G, if we have 120 plus Y, that's going to be 180, and that's simple algebra, so Y equals 60. And if we have D and F, or F and D, they both have to equal 180. Well, one of his 80 is so obviously the next one, you don't probably even have to do the simple algebra to figure out that Z is 100 degrees. Let's move on. Another theorem. If a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Conversely, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter, or the hypotenuse, is the right angle. So, if I translate that and take out some of the words, all that means is that the hypotenuse of a right triangle inscribed in a circle will be the diameter, and the angle across from it will be a 90-degree angle. And if the diameter of a circle is the hypotenuse of a triangle that is a right triangle, it's just the way it goes. So what are we going to do with that? Another example. Find the value of each variable. Given what we know about the theorem we just looked at about the hypotenuse and remembering about right triangles, solve this problem. Pause now. Okay, here is your answer. Ta-da! If HB is a diameter, then C has to be a right angle. Therefore, 2x has to equal 90 degrees. Divide by 2, x equals 45. Very simple math. As long as you can remember what the theorems are, that's the key. Okay. Example 6. Now we've got a quadrilateral. So we've got A, B, C, D inscribed in circle P. Remember what that means based on what the theorem is. If you have to, go back. Find the measure of each angle. We know that 2y and 5x, nice little hint here, and 3y and 3x. They all have to, according to the theorem, equal 180 degrees. Pause now and figure that out. It's going to be a little more complicated than the others. So think about what we know how to solve this. Ready for the answers? It's a little bit more complicated, like I said. Here we go. Now, you can either use substitution or elimination to solve this. And once you recognize that 3x plus 3y equals 180 can be easily divided by 3, that's going to be your answer. So we've got our first equation, 2y plus 5x equals 180, and 3x plus 3y equals 180. We're going to divide by 3, so we get x plus y equals 60. And then we're going to solve for x or y. Now, in the book, they solve for y. I'm going to solve for x. It can go either way, but sometimes people freak out if they see negatives pop up. They don't have to freak you out. So if we have x equals 60 minus y, that's going to be what I'm going to substitute for x into this equation right here. So once we do that, we have 2y plus 5 times what was x, 60 minus y, equals 180. That's when we substitute. Now we're going to have to distribute. So we will distribute 5 times 60 and 5 times negative y. We simplify that. Then we're going to solve for y. And then we're going to take what we have for y equals 40, and we're going to put it right up here in this little equation because that's the simple one. And 60 minus 40 is 20, so x is 20. Then all you have to do is plug them in, their x's and y's, and find out the measure of every one of those angles. If you need to pause, where you will probably make your mistake is sometimes when people distribute, they make a mistake. They don't do 5 times 60 or 5 times negative y. They don't pay attention to that sign, and you have to pay attention to that. It's a big deal. Gives you the wrong answer. Sometimes they simplify incorrectly. So you just have to be careful and check your math first. That's probably where you went wrong. Let's move along. Aha, we're at the quick quiz. So that was the last of the examples. So here's the quick quiz. 1. Why do you know, whoops, looks like a typo there. Why do you know about the measure of inscribed angles? Let me just fix that. What do you know about the measure of inscribed angles? Why do you know about, my gosh, they're all typos. My goodness. What do you know about the measure of opposite angles of a quadrilateral inscribed in a circle? And how do you know about the hypotenuse? Because somebody told me. Let me just change that too. Terrible mistakes. What do you know about the hypotenuse of a right triangle inscribed in a circle? Okay, let's go with the first one. What do you know about the measures of inscribed angles? We know that they are half of the measure of the intercepted arc. Number 2, what do you know about the measures of opposite angles of a quadrilateral inscribed in a circle? We know that the opposite angles are supplementary or equal 180 degrees when added together. Number 3, what do you know about the hypotenuse of a right triangle inscribed in a circle? We know that the hypotenuse inscribed in a circle will be the diameter. All right, that's 10.3. I'll see you for 10.4.